Hello guys, my name is Uday Kalyan here. My roll number is 24AI10014. My contribution to this repository has been creating the PyTorch function main.py, generating the images in process images.py which can pre-process the images, and generating the first four figures of the Wgan paper. Cool. So now here first I'll be explaining how exactly did unsupervised learning come about and how did it go over to GANs and VEs. So what we have here is when we have a bunch of samples xi, we kind of assume it follows a particular real distribution PR, but we don't really know the shape of the distribution, we don't really know the parameters, so we can't really perform any analysis out of it. So what we try to do is we try to assume a distribution p theta, we assume the type of it, and what we try to do is we try to change the parameters of the distribution such that it's as close to PR as possible. This has been through doing it through MLE, which eventually mathematically leads into the KL divergence. However, the issue about KL divergence is that it only checks the overlap between the two distributions, which means in the case of low dimensional manifolds, as in these distributions don't really overlap at all, we can see that this p theta comes out to be 0 and KL divergence comes out to be infinity. Now, how do we fix this initially? We use VEs, where we basically add a certain amount of noise to make sure these two overlap. But the issue is that this noise finally affects the final image too. Now next, what we do with GANs is from the latent space itself we try to make a neural network generate the image, and after that we add another neural network which is a discriminator, and it eventually leads to a minimax game where the generator tries to create realistic images, and the discriminator tries to distinguish what is generated by the generator and what is the real sample. But overall the objective of the paper is to actually create an optimal mapping between theta and p theta such that this loss continues, because that kind of helps the GAN train much more stably. Cool. So what we have here, we have four different divergence functions: the TV divergence, JS divergence, KL divergence, and earth mover divergence. JS and earth mover, which is Wosteen, is focused mostly on GAN, so we'll be explaining that in detail. But this is explained with respect to something called p theta. Here is a direct distribution where basically on the line x is equals to 0, we take y on a uniform between 0 and 1. P theta is the same thing, but however it's an x is equals to theta. What we try to do is now we try to estimate how close are these distributions to each other. Now intuitively, obviously you can assume that if theta is small, that means the lines are close to each other, which means the distribution should be close by. If theta is large, the lines are far away. However, in KL divergence, we can see that it's simply not even finite, it's simply infinite when these distributions are not perfectly overlapping. In TV also, it is simply discontinuous. Now in GS, what happens is that it is also discontinuous here. It's 0 at the point 0. However, at the point at any other distance, it's simply log 2. So we don't really get any continuous function, and it's not really a good estimate of it. In Wosteen, however, it's a very good estimate. It actually gives us the value of theta itself, which means the model tries to make this theta as close to possible and tries to make sure that even if these two lines can't overlap, they try to go as close as possible. Cool. So what this leads to is Wosteen distance kind of helps it form as a critic. A critic basically tells how good is this distribution itself, where a discriminator just shows how much does it overlap. This is much more better because we can see that produces smooth and continuous gradients, and also it kind of helps the model train in a much more stable fashion in lesser steps, because in JS discriminator the GANs can have a huge amount of oscillations. This also Wosteen critic kind of removes the entire notion of mode collapse itself, which happens in GANs. So here we're going to experiment this with a toy distribution. This is a distribution of 8 normals, each on the circumference of a circle uniformly spread apart. What we try to do is we try to make these GANs learn the structure in this distribution. We can see standard GAN simply cannot learn it. Same with unrolled GAN, in which basically we learn the discriminator more than generator. It does try to an extent at some point, but still unable to learn it, and it kind of collapses. In Wosteen GAN, however, it eventually does learn it to a very good extent. It doesn't really collapse. It learns very gradually in a proper fashion. For this experiment, we had to constrain the model parameters to extremely small number. We had to make only 2 layers with 8 hidden units, because anything much more better will kind of lead to any GAN learning it easily. Cool. Our second experiment comes in this toy distribution, where the fake one, the real one is in -5,0 and the fake one's at 5,0. We kind of evaluate the discriminator here when it uses Wosteen and when it uses the normal sigmoid. So, as in GANs. So when we use a sigmoid in normal GANs, we can see that it provides a 0 gradient almost. and then in the middle it blows up, which makes it very unstable for training. Wastine GAN, however, gives us a very stable gradient here. We can see it's much more cleaner. Cool. So now in data preparation, what we have, the primary issue lies in the fact that LSVN dataset has 3 million images, out of which we can't really train 3 million images in the first place. Second of all, the images are roughly 300 cross 300, 300 cross 400. And the paper itself downsamples them to 64 cross 64, which we don't really want to re-download the same thing again and downsample it again and again. So instead, what we do is we took a 10% sample of Kaggle, and then which contains 300,000 images, which we think is decent enough to train the Wgan, and then we pre-process it once locally itself, which compresses it with an 85% compression, which pushes it to 1.2 GB, and then we simply upload that to our Kaggle notebook, which you can use again and again, making it much more efficient to train. And here are the results. So this is the direct distribution one. We kind of make a synthetic sample of 0 to kind of show how it is. This is the one with the 3 GANs around the for the normals, and this the gradients for these 2 normal distributions. And here is the analysis of different architectures for WGANs with DC GAN and MLP. And that ends my part here.
Um, Hello, my name is Arjun Desai. My roll number is 24AI 122, and I will be presenting the part of limitations of GAN and the how WGAN solves some of those problems. The first problem in GAN is the training instability. What happens is when we are training generator and discriminator gets good at the discriminating between the real and fake images very fast, well, faster than the generator gets at generating them. So what happens is that this kind of curve is produced, uh, because of which uh, because of which at the end cases the gradient becomes near zero, and our and the information relayed by that becomes negligible. Uh, the second problem is the mode collapse. Because of the loss function we choose, it this, it is more focused towards getting a right answer. So what the generator does is, suppose we have CIFAR 10 dataset. The generator gets very good at making seven, so it will only make seven after that. So after that, discriminator will also get good at discriminating between sevens. So then the generator will change from 7 to suppose 8, and this oscillation will continue. Because of which we won't have much wide options between generations. We can see that in we trained a GAN model from scratch on the LSUN dataset, and we can see there are many similar images generated. This is a showcase of the mode collapse. The third limitation is the no JS divergence is not a good loss metric. What do we want in a loss? Loss should decrease with the training time, which will signify that the images are getting better. Uh, at least we can seeing the loss, we should be able to say that the images are getting better or worse. But as you can see, this is the whole time period of the GAN training, and the loss approximately stays constant. Yes, it sometimes goes down, but it largely stays constant, which is a signifier of that loss doesn't reduce with time. And the last problem is the Nash equilibrium problem. GAN is training between two minimax pairs. Generator tries to uh, maximize the loss, and uh, the discriminator tries to minimize it. This problem has its limitations. Now we will see how, the advantages of WGAN, how WGAN solves some of these problems. First, as we can see in the figure before this, um, the in the edge cases, uh, the gradients become near zero. But if we use Wgan loss, then Wgan critic, then the loss, then the gradient doesn't go near zero anywhere. Which because of this, the loss will the gradient will have more information, because of which the training will be more stable, and the generator won't be confused by the discriminator. Huh. The second advantage of WGAN is because of the GS loss, the model is forced into getting the picture exactly right. What WGAN does is first it tries to get in the vicinity of the uh, correct uh, uh, correct options, and then it zeroes down on one distribution. Because of this, the mode collapse problem reduces significantly than GAN. And as we saw, the GS loss doesn't reduce throughout training. This problem is not carried in WGAN. The Wasserstein loss correlates with visual quality. As the loss goes down, the visual quality of images also increases. So this is a better signifier of how the images are getting produced. And the last advantage is, if we train a GAN without batch normalization, the output images are not at all satisfactory. This doesn't happen with WGAN because it gives a stable, accurate signal to learn from rather than chasing a moving target. These are the limitations of GAN and how WGAN solves it. Thank you.
My roll number is 17. So my part is WGAN core idea, in which standard GAN uses JS divergence to compare real and generated data. So the problem is, in the beginning of training, generated data are just noise. So real and fake distributions are very far apart. Because of this, discriminator will be too strong, like very quickly. So it separates real and fake samples and then stops giving gradients to the generator. So this makes the training unstable and generator does not improve properly. So Wgan fixes this by replacing JS divergence with Wasserstein distance. Instead of checking whether real and fake are different, Wgan measures how far they actually are. So this gives more useful learning signal and makes training more stable. So here comes the next part, Wgan training algorithm. So DevilGAN changes the GAN training process in few important ways. So the first one is discriminator becomes a critic. So it doesn't output a probability. Instead, it will output real valued score. So final sigmoid layer will be removed. And the second change is critic is trained 5 times for every one generator update. So this will help the critic in learning better estimate of Wasserstein distance before updating the generator. So the third change will be Debilgan uses RMS prop instead of Adam in the original paper. The most important change is weight clipping. So after every critic update, its weights are clipped to a small range, like usually between minus 0.01 to 0.01. So this is done to enforce the Liplett's constant, which is the required criteria for Wasserstein distance to work properly. So in the Devilgan loop, we do this. We train critic multiple times, clip the weights, and train generator once. So this slide explains why Devilgan is more stable. Since Devilgan gives better gradients to the generator, that makes it more stable. So in standard GAN, once discriminator becomes too strong, loss will saturate and gradients will become very small. So this causes vanishing gradient problem. This will make generator to stop learning properly. So Devilgan avoids this by using Wasserstein distance. So Wasserstein distance changes smoothly even when the generated samples are still poor. This will imply that critic can still give gradient information even when real and fake distributions are far apart. So by this, generator will get a clear direction on how to improve. So another advantage is Deblugan loss is meaningful. In standard Deblugan, loss often do not match the image quality, but in Deblugan, loss usually reflects the sample quality much better. So overall, Deblugan is more stable because it gives smoother training and more useful gradients.
My name is Aditya Rakra, and I will be walking you around the repository that we have created about Wgan. So let's begin. Um, so the heart of this code is main.py. What this does is that it supports multiple architectures such as convolutional GAN and MLP layer GANs. The data sets that we will be using, there are multiple data which can be used like CIFAR10, LSU, and ImageNet. Also, you can use customized folders. That is not no issue in this one. But there is a wet clipping implementation deployed. So as you can see, when in the argument parsers, there are multiple arguments that are being taken. First is data set, then data root, batch size, image size, input channels, size of Latin vector, also learning rates, beta function for Adams, and then and that's this one. This is the clamp function, clamp part. So for clipping, this will be used. Also, the training loop will be there with separate critical iterations. Uh, so this is for different data set. You can directly pass it from the command line, and this we have to enter Spartan, and it will start working on Spartan. Um, and this is the weight initialization function for so that weights can be initialized before starting the loop. So at we are using Atom Optimizer in this one, and RMS prop or if Atom is not available, then we'll be using RMS prop. Also, the iterations are not kept that high. 25 iterations at max will be there, and we'll be saving the main iterations to locally. So the main part of this code is this one. This two codes are the implementation of different structures. So this is the convolutional discriminator structure. What this involves is that there are multiple convolutional layers, like this is con 2D, batch norm, and Liquid. So there is no, the main important part is that there is no batch normalization in this critique, which was a crucial assumption for the Lipschitz constraint that we discussed in the paper. Uh, so this code is like basic convolutional layer, which will be deployed for the number of extra layers that will be inputted from the command line by the user. So that is a basic one. Also, this generator part. Generator part is the transpose convolution network. So other than convolution network, we are using a transpose convolution network so that we can generate it. So this is in order so that the generator and distributor are working oppositely to each other. So that a kind of symmetry must be maintained between both. And yeah, the no batch normalization constraint is also there in this one. This one. It's the same thing, but just so that there should be no batch normalization, there are a bit of changes. Same with MLP layer. MLP layer will be a simple uh, perceptron. So it is not that deep. This is the basic structure of that. This is the generator part. Then there will be discriminator part. Yeah, they are almost similar, as you can see. Next part of the code is generate. So what we'll be doing is that there we will be loading the generator configurations in this one. and we'll generate new samples from random latent vectors. So this will be useful for the post-training evaluation, so that we can check if the output is working correctly or not. So yeah, that is our notebook. Thank you.